The quantum mind, new evidence for consciousness beyond classical physics. Recent experimental findings have rekindled interest in one of neuroscience's most controversial theories, the quantum basis of consciousness. As explored in Anton's research, this emerging evidence suggests that the boundary between quantum physics and neurological function may be more permeable than previously believed. The quantum consciousness hypothesis has its roots in the work of physicist Roger Penrose, who proposed that consciousness emerges not merely from classical neural computation, but from quantum processes occurring within neurons. Penrose, 1989. This radical departure from conventional neuroscience faced immediate criticism due to a fundamental obstacle. Quantum coherence typically collapses rapidly in warm, wet environments like the brain. Tegmark, 2000. Anesthesiologist Stuart Hameroff expanded Penrose's framework by identifying potential quantum structures within neurons. Hameroff noted that certain anesthetic gases like xenon and krypton induce unconsciousness through mechanisms that remain poorly explained by conventional biochemistry, suggesting possible quantum interactions. Hameroff and Penrose, 2014. More significantly, he proposed that microtubules, cylindrical protein structures within neurons, could serve as quantum processors rather than mere cellular scaffolding. Together, Penrose and Hameroff formalized these ideas into the orchestrated objective reduction, Orch-OR theory, which posits that 1. Microtubules generate quantum states, 2. Anesthetics disrupt these quantum states, and 3. Gravity ultimately collapses these states, producing consciousness. Hameroff and Penrose, 1996. Despite widespread skepticism, recent experimental evidence has provided unexpected support for aspects of this theory. A 2023 study demonstrated that anesthetics directly alter microtubule fluorescence, suggesting a previously unrecognized interaction between these consciousness-altering compounds and the very structures Hameroff identified. Craddock et al. 2023. Even more remarkably, recent research has shown that organized microtubule networks can exhibit superradiance, a collective quantum optical effect previously thought impossible in biological systems. This finding suggests that microtubules might indeed sustain quantum coherence, a prerequisite for any quantum theory of consciousness. Solardo et al. 2023. While these discoveries don't definitively prove quantum consciousness, they provide the first experimental evidence that biological structures can support quantum effects, potentially bridging the seemingly insurmountable gap between quantum physics and neuroscience. As Anton's research highlights, we may be witnessing the first empirical validation of a theory long dismissed as scientifically implausible. The implications extend beyond neuroscience, potentially transforming our understanding of biology, physics, and the fundamental nature of conscious experience. Further research will need to establish whether these quantum effects can meaningfully influence neural processing and whether they contribute directly to consciousness. What remains clear is that the brain's complexity continues to challenge our most sophisticated scientific models. The possibility that consciousness emerges from quantum processes within microtubules represents a paradigm shift in our understanding of the mind, one that could ultimately reconcile the subjective experience of consciousness with the physical laws that govern our universe.